So, good morning. This is Venkasara. Today, our topic is moving charges and magnetism. This is our topic. Moving charges and magnetism is our topic. So, in this chapter, we know that uh, charge is a static. When the charge is in static, it cannot pass from one place to another place. But the charge is moving from one point to another point, so then it will be considered as current. Okay, anyhow, so Ørsted first 1820 he observed that when the conductor is in a conductor, the electricity is passing, the current is passing in a conductor. Here the conductor is C. Here this is a conductor. So it's look like this. But if in other direction, if you see, so the wire is a conductor. Okay. So this point I considered as this in the page. It was written this. In this conductor, the electricity is passing through it. Okay. The charge is moving. Okay. It shows. So he observed that when he placed a magnetic needle. So this is a magnetic needle. He kept near to it. Okay. Like this. So what he observed is, so whenever he kept a magnetic needle near to it, then it gets deflected. Here the black one is a north pole. This is a north pole, and this is the white portion is south pole. Okay, when this is a conductor, so it was shown like this. Okay, how it was shown, actually this conductor is coming from the page. Okay, this coming, see, so imagine this is the screen. So when a wire is coming from the screen, computer screen, it shows like this. If it was going if the current flow is going into the screen, then it is considered as then I am showing like this. Okay, so likewise, when a conductor moving a charge, carrying a conductor, so when we place the magnetic needle near to it, then it gets a deflection. Okay, if the flow is in reverse direction, that means if the current is moving, if the charge is moving in this direction, then what happens? The direction is reversed. Means, so the magnetic needle is showing in a reverse direction. Okay, likewise, this was first observed by the scientist Ørsted. O-E-R-S-T, Ørsted. Okay, so this scientist observed this. Okay, so this is first he got from the relation between the moving charges and magnetism. So when we sprinkle the iron fillings around the conductor or around the magnet, what happens? The iron fillings around the magnet arranged in a particular proper manner like this. Okay, so in an order, the iron fillings around the magnet, around the bar magnet, it's showing like this. Okay, when we twinkle, this is the north pole and this is south pole. So around like this. So this is how this happens. The electric field, the magnetic field near around the magnet make like this. Iron fillings are arranged in a order. Okay, likewise. So when a conductor is carrying a conductor means current, the magnetic needle around near to it, it gets the deflection. If the flow is in reverse direction, so this is also in a reverse direction. Okay. So theoretical and experimental investigations indicate that moving charges produce not only an electric field but also magnetic field in space. Not only an electric field in the on the earth, but also in the space also. Okay. What shows the electric field? The electric field and magnetic field produce both mutual understanding. Means the once the electricity flow starts, then automatically the magnetic field also gets produced, not only in the earth but also in the space. Whenever the current is flowing, then automatically magnetic field generates near to it and opposite to it. Okay, this was the first assumption made. So some assumptions also made like this. The magnetic field produced by current carrying conductors or by moving charges. Okay, and the second assumption is the forces exerted by magnetic field on moving charges or on a current carrying conductor and a torque exerted on a coil carrying current. And the third option is the electromagnetic induction, that is effects of changing magnetic fields and changing magnetic fluxes. And the fourth one, last one, is direct and alternating currents through various circuit elements. Okay, these are the assumptions made by them. Okay, so now I'm going to explain the Oersted experiment. Okay, so in this experiment, this is the conductor. Means conductor here is the rod of this. Okay, this conductor is I am showing in this conductor I am showing in this direction. Okay, so around this direction I am showing like this. Okay, imagine that the current carrying conductor perpendicular to the plane of the paper. Let the direction of the current be out of the paper, normal to the plane of the paper. Okay, so it's showing like this. If it is in reverse direction, means that if it is inside the paper, so I will show like this. Okay, so I will show like this. Now, the direction of magnetic field around the current carrying conductor, the direction of magnetic field around the current can be determined by the following rules. There are four rules are there. There are three rules are there. So, with the help of the three rules, the direction of magnetic field around a current carrying conductor can be derived or can be determined. First one is Maxwell's corkscrew law. So this is a corkscrew. So this is a corkscrew law. Okay, I will change the color. So this is a corkscrew corkscrew. So have you ever send a corkscrew? See, nails are there. Some nails have corkscrew. Means so some nails like this. There is no corkscrew. Okay, direct nail is there. So there is a sharp needle is there. So you can if you hit the to the wall, then directly it goes. But some of the corkscrew, some nails are like this. So it gets some screws are there. It's screws are there. These screws are just like this. Okay, and the screws are there. So if you want to send the nail into the wood or any wood or into the wall, in which direction you turn it in a clockwise direction. You turn it. See the clockwise direction. That means so this is sorry. This is the cork screw. So screw. If you turn this like this, okay, in a clockwise direction, the cork screw go into the wood. Okay, if you move this in a direction of clockwise direction, if you press the nail into the wood, suppose if the wood is there, then if you if you want to move and fix this nail into the wood, then in which direction we will move in a clockwise direction. Okay, if you move in a clockwise direction, then automatically this screw move deep into the move into the wood. If you move in an anti-clockwise direction, then what happens? It can remove from the wood. Okay, na? So in this way, then the direction of rotation of the screw had given the direction of the magnetic lines of force. Okay, and the second one is right hand rule. Fleming's right hand rule. So in this direction. So this is the third one. Third one is right hand rule. So imagine the current carrying conductor is held in the right hand. Okay, so the direction of current indicated by the thumb. Then the folded fingers indicate the direction of magnetic lines of force. That is B. Magnetic lines of force B. Okay. The direction of current is induced by the current. So this is the thumb is the direction. Thumb shows the direction of the current. Okay. Magnetic lines. Okay. Magnetic lines of force B in a this direction. Okay. this is in this direction, that is in the current direction is this direction, and magnetic force lines direction is in this direction B. Okay, na? Now the third one, and this is the first one, this is the second one, and the third one is Ampere's swimming rule. So for this Ampere's swimming rule, see, so I'm drawing one magnetic needle. Okay, so this is a magnetic needle. Okay, this is a magnetic needle. This is a north direction. This is south direction. Eh? So imagine one person is moving. So this is the I direction. One person is swimming with left hand and right hand. Drawing the diagram is difficult to me. So this person swimming on the pond, the swimming pool, in the direction of I, current direction I. Okay, then the magnetic field. Okay, then the current facing a magnetic needle. Okay, as shown in figure. Then the north pole of the needle will deflect towards the left hand. Okay, the north pole will, here the north pole, south pole, north pole is there. The north pole is in left hand direction. Okay, the pole of the magnetic needle deflect towards his left hand. So in which direction it deflects? North pole deflects towards to the left hand side. Okay, and the south pole deflects towards to this direction, south direction. Okay, na? The direction of deflected magnetic needle reverses when the direction of currents reverse. Means, see, if the direction is reversed, means if the swimmer is in moving in the direction, then this direction will be this side and this direction will be this side, the magnetic needles. Okay, so this is the introduction of the moving charges and magnetism. Okay, so uh, I'm stopping this. Okay, so now thank you for watching this video. Okay, stop it again. Okay.